All right. We are now recording. Let's get from current slide, and we'll be ready to go. Wait a minute. I messed something up. Let me go back. For some reason, I thought I clicked on the thing there, and nothing came up. Okay. For example 5. All right, that's where we began today. Now we'll go from current slide. Okay. Let me go over just the few announcements. I think you've heard them all before, but just as a reminder, and also for people who aren't here, if you didn't hear, hopefully you'll be listening to this. Because of my appointment on Tuesday, which went quite well, thanks, we're meeting early. We met early Tuesday, today, and next Tuesday, okay? And then we'll be through with the 8:15s and back to 8:30s. All right? But my trig class wasn't any way to do that because they're right after this one, and several of the students had classes right after that one. So what we're doing with that is meeting tomorrow. So rather than being on the Birmingham campus tomorrow from 8 to 12, I'll probably be on this campus. I'm going to try to be here 8 to 12. However, I do know there are some things that probably are going to be due tomorrow, and I probably will have to run those by the Birmingham campus. And unless I can do that just on my way home, I may have to either come in by the Birmingham campus. Cody's here. Okay. And take care of some things there before I come out here for the 9 o'clock class, or after 10:15 when the class is over, I may have to go either to Birmingham or back to Birmingham, one or the other. It just depends on how things fall out for tomorrow. So I don't know. I know I'll be here from 2:55 from 9 to 10:15. Before that and after that, I'm not sure where I'll be. Hopefully I'll be on this campus in my office. But if I have to go to Birmingham, I'll do that as well. So you just have to call first. And if you can't get me either number, just keep calling. But don't call between 9 and 10:15 because I'm not going to be either place. And don't bother leaving a message because I don't know if my voicemail is working properly, and the other one I can't access. So just call periodically. When you catch me on one of the campuses, then I'll let you know where I'll be and how long, if you need to see me tomorrow. All right, the other announcement, I made this one before, but just so you'll know, starting this week, which started Tuesday, my Tuesday, Thursday office hours are now extended from 11:15 to 3:15. First mini term, I had Tegan, there you are. Okay. All right. Hey. I'm sorry. That's all right. Okay. And remind me. Amaya, got it. Thank you. All right. And Bree, got it. I know you're in here. Yeah. There you are. All right. Did I get everybody's name when you came in? Okay. I know I saw Tegan. Did I mark you? Yes, I did. Okay. All right. So I was just saying my office hours on Tuesday, Thursdays are now 11:15 to 3:15 because my second mini-term physical science class has delayed start till 3:15 because I have automotive students in it and they don't get out of their block schedule until 3. So more office hours on Tuesday, Thursday, doubled them, which means I'm here till 7:45 at night. Okay, so that's fine too. All right. Those out of the way. Any questions on anything we've covered so far? Okay. We had talked about Easier ways to find the maximum and minimum of a quadratic function. What was that way? Second? An easier way to find the max or min of a quadratic function. Before, we got the quadratic function in standard form, and then the h and the k told us where the vertex was. Okay? And the vertex, of course, will be the maximum if a is negative, the minimum if a is positive. Okay? But there is an easier way than going through all that. And what was that way? We did it last time. It deals with the x value of that max or min, which of course is the h value, an easier way to detect it. Anyone remember what that was? Sort of reminiscent of the quadratic formula in many ways. Okay, the h, let me get, is it, huh? Okay. Yeah. Got it right there. All right. I think I heard in the background, whoops, I still didn't get my pen back. Okay. The h is equal to minus b over 2a. Every time. Yes. I'm sorry? I can't hear you. No, that was Tuesday. Okay. And Cameron's here. Dream on. No, I mean, all right. Cameron is here. Yeah. Tuesday, I had a doctor's appointment, so I had to leave at 9. But now we're making up for lost time. Okay. So your h, they call it x. Guess what? That's your h. It's always minus b over 2a. Now, what are a and b? What are a and b? They are the constants that are in the, I don't want to say standard form, but the regular form of your quadratic function. Not the standard form, but the regular form. So here is an example taken from America's Sport. The path of a baseball after being hit is given by this function. F of x is equal to negative 0.30032 x squared plus x plus 3, where f of x is the height of the baseball in feet, and x is the horizontal distance from home plate, also in feet. Okay? So we're looking for what's the maximum height of the baseball. Now, all right. Here's Ashley. Oh. So I put an A by your name because you started with Ashley. That's an absence note. I got it. All right. Anyone else come in that you didn't hear me acknowledge your presence when you came in? All right. Now, you might say, where did such a weird-looking equation come from? And you don't need to know that to do the math, but let me just explain it to you. Notice here, you're dealing with feet, okay? And here you have this really weird number here, okay? Well, that really weird number has a 32 in it, and it just happens to be that the acceleration due to gravity in the U.S. customary system is 32 feet per second squared. That's where the 32 came from. Now, it has all sorts of other things here. Part of that is the speed that they're assuming that you hit the baseball and that kind of stuff. Okay? Now, one other issue here, where does the 3 come from? Well, expert on hitting baseballs, where is the sweet spot for hitting a baseball? Approximately, on average. Up here, down there, about the waist, which is about 3 feet off the ground, right? So that's where the 3 came from. You're assuming they hit the ball 3 feet above the ground, because remember your f of x is your height above, the height of the baseball. So when x equals 0, that's where the baseball was, 3 feet, right about waist, right about where you were going to hit it. Smack that thing. Okay. So you tell me, how can we, okay, what is the maximum height? That will be the, okay. Will that be the vertex, or will that be something going to infinity, or what? What can you tell me? What information does this give you? It's what? Yes, opening downward. So therefore the maximum height will be your vertex. Exactly. And h is the x-coordinate of the vertex. Okay? That won't tell you the maximum height, but it'll tell you where the maximum height occurs on the x-axis. And how do we get that? Hint, hint. Oh, I didn't know. What is that negative 0.0032? What would we name that? If you, in terms of the letters you see up there on the board. That's your A. What's your B? Say again? 1. The B is 1. The A is that thing. So now we just plug it in, plug it in. Your H, or the x-coordinate of the vertex, is minus, and your B is one over, and what's your A? Oh, 2 times A. And what's your A? Negative 0.0032. Okay? Weird looking number. Okay? Now, it's not too hard to deal with, though. First, I'm going to deal with the signs. There's a negative, there's a negative. 2 negatives make a positive. So I'm not going to worry about the signs anymore. Okay, so the height is going to be positive. You dug it into the ground. That's good feeling, right? So, what you have now is 1 over 0.0064. Pull out the good old calculators and see what that gives you. Or you could have pulled out the calculator at the very beginning and not done any of the things I've done. Say again? Okay, 156.25 you said? Okay. And here's running. Okay. Anyone else come in since I called roll? I got you, didn't I? Yeah. Name, please? Huh? Alexi, right. Hill. Right? Alexi Hill. Okay. All right, anyone else? Okay, I missed you when you came in, sorry. So, and this is measured in feet. And what does that indicate? Is that the height of the ball? No, the H is the horizontal distance from home plate in feet. So how do we get the vertical? That's what we're interested in, the height of the ball. In other words, we're interested in the K. Now that rigmarole we went through last time had a really awkward, nasty combination of things to get your K. Let's not use that one. Let's be lazy and use the easy way. And what would that be? What is your height? Your F of X. So let's take the F. Goodness, I can't write. I say F and write H. There's something wrong upstairs, okay? All right. We're looking for F of 156.25. If you still got that on your calculator, you can just live with that. And here's Jake. Okay. All right. Anyone else come in since I called roll? This will give you the height. So that'll be negative 0.0032 times 156.25 squared plus 156.25 plus 3. Don't forget your plus 3. Okay? Looks like another good job for a calculator, doesn't it? I'm not going to do that one in my head. So someone punch that in to your calculator or phone or whatever. Now, let me warn you about something, I don't think anyone would do this, but as you're punching, pressing, entering, it's Alexius, right? Let me see if I can get to you from here. There you are. Come across there. Okay. All right. If you're pressing the numbers in, however your calculator takes it, some of the older calculators you have to enter the number first and then change signs. The newer, more modern ones, you can just start with the negative sign. But be sure it's the negative sign in parentheses, not the subtraction key. That's the subtraction. Negative in parentheses is the negation key. So it's negative 0.0032 times 156.25 and immediately hit square. Don't put an equal in between there and square it, otherwise you're squaring the wrong number. But if you do the 156.25 squared, then you can do the plus 156.25 and plus 3. Just like you read it, that should work. Now, older type calculators are cheapies, don't always follow the rules of order of operation. Most of the modern current ones do. I don't know what cell phones do, okay? I think they usually do it pretty well. Anyone get an answer yet? 81.125 feet. That's how high it is, okay? So Cody, probably don't try to catch it at its height. I don't think you can jump quite that high. Okay. So, there's the maximum height of the ball. I think it'll make it in the Superdome with no problem, okay? Won't hit the ceiling. Any questions? Okay. Let's see how they did it. Do I need to leave it up a little longer? Are you okay? Anyone have any problems with the calculators? I see a lot of them still working. You got it. Okay, good. All this stuff's in the way, isn't it?
What did you use to get that second?
So on the button.
What did you use to get that second equation to work it out?
Okay. Now, what this function tells you, f of x is equal to blah, blah, blah. Okay? The f of x is the height of the baseball. So that's what we want to know. The x is the horizontal distance. That's what your h told you. At the maximum height, you were that many feet from home plate. So we take this number, plug it in here, so we plug it in there and there. So that's where this equation came from. Does that make sense? Any other questions, uncertainties? Everybody get your calculator and give you that answer? Okay. Because, believe me, some calculators have different syntax from others. So you have to know your own calculator. You don't want to be learning it at test time. Okay. Now, do you like this better, or would you have rather done this problem getting it in standard form? I think not. Okay, because the first thing you would do is factor out that of the first two terms. That would have left you a denominator here of a negative 0.0032, which we wound up with here, but that would have been a real, and then you take half of that, and then you square that. Oh, yeah, okay. It would have worked, but it's a lot more work. This way, pretty straightforward. Okay, just like quadratic formula, much easier to use to solve a quadratic equation in standard form than it is to do completing the square and going through that rigmarole. Okay? Got it? Okay. So let's see how they do it. Let me delete my scratch and see what they do. For this quadratic equation, here they wrote it down in standard form for, let me call it the normal form, okay? F of x equal ax squared plus bx plus c. So your A is the negative 0.0032, the B is 1, and the C is 3, which we don't really care about right now, okay? We'll care about it later. So, implies that A is negative 0.0032, and B is simply 1. When you don't see a coefficient, understand it to be 1. Make sense? This is all you need to find your H, the X value at the maximum height, at the vertex, okay? Because A is less than 0, the function has a maximum value at, it doesn't, oh yeah, okay, got it. Because A is less than 0, that means it's going to be a maximum value. That sounds like what it's asking for. What's the maximum height? That's going to be the maximum value. And that's going to be when X is equal to minus B over 2A, which we're not going to call it what it is. That is your H. That's where it is, okay? So the baseball reaches maximum height when X is equal to minus B over 2A. You plug in what B is, 1. A is negative 0.0032. And the two minus signs go away. Do the math, and you get 156.25 feet from home plate. Exactly what y'all got, okay? That's how far you are. Remember, the X is not the height. That's how far you are from home plate. To find out the height at that position, go back to your function that tells you the height, okay, when you enter the distance from home plate. So when you enter 156.25, negative 0.0032 times that 156.25 squared, big number, plus 156.25 plus 3 will give you maximum height of 81.125 feet. Now, the physicist in me really gripes about this a little bit because our original problem gave at most 2 significant digits. The 0.0032 only has 2 significant digits, but zeros aren't significant. So how in the world can you have an answer that gives you 5 significant digits? You can't, or you shouldn't. You should round that and say approximately 81 feet. Okay? That's how you deal with measurements. You can't get more precision out of a problem than you put into it. Okay? So, that's just a little gripe of my part. But this is the mathematician who wrote the book, not a physicist. Okay? You should be happy. Okay? Any questions on that? And that is the last slide in the section. There is a checkpoint, however, and it's a good idea to do the checkpoint as soon as you can after class. So let's do the vocabulary. Top of page 120. Linear, constant, and squaring functions are examples of blank functions. Linear, constant, and squaring functions are examples of blank functions. Look at the... Say again? Not quadratic. Only the squaring function would be a quadratic. For quadratic, the maximum exponent is 2. Linear and constant functions, linear is 1, constant 0. Okay? Look at the title of the chapter. And right above, polynomial, exactly. It's the polynomial functions. Okay? I guess you guys can. All right. Number 2. A polynomial function of x with degree n has the form of f of x equal a sub n times x raised to the nth power plus a sub n minus 1 times x raised to the n minus 1 power plus dot, 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 all the way down to a sub 1 times x to the first plus a sub 0, of course, times x to the 0 would be 1, as long as a sub n is not equal to 0. Where n is a blank blank. For it to be a polynomial function, what must n be? What? A blank blank. What must n be? The metric is here. N must be a blank blank. What is a blank blank? Okay? For it to be a polynomial function now, think about what those exponents have to be.
Greater than
Okay, they just have to be, they can be 2, but they could be 1. Okay, because this is any polynomial function. Positive is one thing. What's 1, 2, 3, 4, 5? What do we call those? Say again? They are real numbers, but can you use 0.732? That's a real number. Okay, rational would be 7/3. Can you use that? They are rational numbers, you're right. But specifically, what are they? Their whole numbers would be one thing. You wouldn't even need the positive then. When if you use positives, positive integers. Counting numbers, whole numbers, any of those would work. Okay? So the exponents have to be, cannot be fractions, cannot be decimals, cannot be negative. Okay? For a polynomial. Number 3, a blank function is a second degree polynomial function and its graph is called a blank. Someone answered it. Quadratic function and its graph is called a parabola. Got it. Excellent. Number 4, when the graph of a quadratic function opens downward, its leading coefficient is blank. Say again? Negative. And the vertex of the graph is a maximum. Okay? A maximum. Okay? It could be negative, but still be a maximum. All right, homework exercises. You've heard most of these before. I would do all 4 of 5 through 8. Okay? They only have answers and descriptions of them at calcchat.com for 5 and 7, but you can do all 4 of those. Then do either 9 or 11. They're both at CalcChat. 9's at CalcView. Do any of the odds, and here's Ryan, right? I've just got to find you now. I know you're in here. Don't try to hide. Okay. There you are. All right. Anyone else come in since I called roll? Okay. So as I was saying, any of the odds 13 to 25, they're all at CalcChat. 17's at CalcView. Then do any of the odds 27 to 33, they're all at CalcChat. And do 35, it's at CalcChat. Any of the odds 37 to 45, they're all at CalcChat. 37's at CalcView. Do either 47 or 49, they're both at CalcChat. Do any of the odds 51 to 55, they're at CalcChat. 57 to 61, they're all at CalcChat. 57's at CalcView. Do either 63 or 65, they're both at CalcChat. Try doing 67, okay? And then some applied problems, any of the odds 69 through 73. They're all at CalcChat. There's some true-false, number 75. It should be at CalcChat. And then there's a think about it problem, so you can think about doing them if you want to. And that's at 77. And verifying a vertex is at 79. They both should be at CalcChat. Now, 81's a proof, so if you're really into proving things, especially you math majors, you may find this exciting to do, 81. And that should have a be at CalcChat as well. All right, any questions on 2.1? Okay, we're going to finally leave it and go to 2.2. Okay, 2.1, we dealt mostly with quadratic functions. They're polynomial functions, maximum exponent of 2. In 2.2, we're going to deal with polynomial exponents, yes. They have recently gone in and changed these things, so there's no way we can get into this. I don't usually teach in this classroom, so I hadn't tried it, but they don't let me into it. They know I'd fiddle with it, okay? Now, it was so bizarre. Yesterday morning in 2:55, they actually had the heat on. I said, wow. And then I came in here this morning, and they still got air conditioning, and it's cooler this morning than it was last time. So it's probably on a different system. I wish I could do something, but I can't. I'm chilly up here too, and I'm usually not chilly. Okay. All right. So let's go to current slide. So we're still in Chapter 2, Polynomial and Rational Functions, but now 2.2 will be dealing with polynomials, functions of higher degree, 3 or higher. Okay? Now, our objectives here to use transformations. Remember those? Shifts, up and down, right and left, stretches, what was the other one? Shrinks, stretches and shrinks. For reflections, use those kind of things. We will use a leading coefficient test, which I don't like to call the leading coefficient test. I'll explain that to you later, to determine the end behavior. What's going on when you're going to very small values and very, very large values. That's what we'll do there. I like to call it the leading term test, not the leading coefficient test. And we'll find and use the real zeros of polynomials functions as sketching aids. Oh, yes. Okay. And the final one, we'll use the intermediate value theorem to help locate real zeros of polynomial functions, which is something we're going to pick up and go with in the next section, finding the zeros. So let's look at the graphs of polynomial functions. All right. In this section, we'll study basic features of graphs of polynomial functions, not the specifics so much, but the basic features. Okay. First feature is that all polynomial functions with exponents, positive whole numbers, positive integers, they're always continuous. Always. If you throw an exponent being negative, put it into the denominator, that probably don't have a discontinuity. Okay? If you put a root in there, there's a good chance you're going to have places where it's not defined. But a polynomial function, as long as those exponents are positive integers, they will always be continuous. That's one feature. There is another one. Essentially, this means the graph of a polynomial function has no breaks, no holes, no gaps. That could be a polynomial function. Nice, continuous curve. Okay? Now, what they don't say here, and I'm going to go on and jump on it, all indications are this continues down this way forever, and that continues up that way forever. It could be this could come up and turn, or that could go down and turn, but the way they've drawn it makes it appear that's going to go down like that. Now that tells us something. We'll wait till we get there, but that tells us a few possibilities about that polynomial function. The deal they talked about there is continuous, no breaks, okay? No holes. This, what you think? Say again? Yeah. I got to get around to you. This is so much fun. Okay. Good deal. Okay. Would that be a polynomial function? Yeah. Okay. Now, that may be a piecewise defined function, that each piece could be a polynomial, but it is not a polynomial function. It's a piecewise defined function. Defined one way from there and another way from there. Not the same continuous polynomial function. That has a gap. Okay? The second feature of all polynomial functions is not only are they continuous, they're smooth. What do we mean by smooth? That all the bends and turns and things like that are gradual. Okay, now that's pretty sharp there, but still it's rounded. That's certainly rounded. That's rounded. That's rounded. Okay, then it looks like it's going up here and going down there indefinitely. Okay, now what it's not is pointed. That's not smooth. It's not got a cusp in it. That's not smooth. It's not got an angle in it. That's not smooth. It's all rounded. So the two features, smooth and continuous. All graphs of polynomial functions are smooth and continuous. That is both. Okay? Now, Would the absolute value function be a polynomial function? No, it's pointed. Okay? It meets at a v. Can't have it. That won't work as a polynomial function. It's a piecewise defined function. Okay. So that's the absolute value function. Polynomial function cannot have a sharp turn. It must be a nice, smooth, rounded turn. Okay? In other words, if you're driving it, you could drive it continuously. You couldn't stop and make a sharp turn. Not allowed for a polynomial function. That's not one. Okay? Once you get into calculus, there'll be a lot easier way to say this, but this is fine for now. The graphs of polynomial functions of degree greater than 2 are more difficult to analyze than the graphs of polynomials of degree 0, which we call what kind of function? Polynomial of degree 0. Constant function. Degree 1 we call a, no, 2 would be quadratic. 1 would be linear. Okay. All right. So higher degrees, a little bit harder to define. However, there are features, and we'll talk about them in this section, coupled with your knowledge of point plotting, intercepts, symmetry, and all that kind of stuff to make reasonably accurate sketches by hand. Okay? Polynomial functions that have the simplest graphs are those of the form f of x is equal x to the n. Now, we have a name for that kind of function. We call it a power function. Okay? But we're letting n only be integers greater than 0. No negatives, no fractions, no decimals. They're all integers greater than 0, just like we were saying before. Okay? And those are all of those are power functions, but these are specifically power functions. Now, yes?
What do you call a graph with negative exponents?
Okay, say that again.
What would you call a graph with negative exponents?
Oh, I'm just kidding. Okay. We'll talk about those. Sometimes your rational functions are like that. That's what we're going to do in section 6. Okay? But always when you put a variable in a denominator, which would be a negative exponent, then you have places where that could be 0. And you have to disallow dividing by 0. So that's what makes them a little more difficult. But you can find that out and analyze the graphs of those pretty well too. So we're going to deal with polynomial functions first, and then we'll pull in those with negative exponents later. Okay? Good looking ahead question, though. All right, I haven't turned the page as I should have. Now, let's look at a few of these functions of this form. This harkens back to section 1.6, I think it was, when we did the parent functions. Remember that? Okay. Sort of what we're going to be doing here. The basic functions at these various levels. Okay? I want you to notice a few similarities here. Here's your quadratic function, your simple squaring function. Y is equal to x squared. That's the gray line here. We know how that looks, right? When it's that, we know that 3 points automatically, 0, 0, 1, 1, and negative 1, 1. Put them in, you see those are obvious ones. Other points are easy to do too. Okay? Now let's jump it up, not 1, but 2, and do x to the 4th power. Okay? Now, it has the same 3 points, 0, 0, 1, 1, and negative 1, 1. Okay? But here's the difference. Past this 1, it goes up much more sharply than the parabola did. In between minus 1 and 1, it's quite a bit flatter than the parabola was. Okay? And it goes on from there. If you put a 6 there, x to the 6, that would be even steeper out here, longer time flatter here. 8, 10, 12, it just follows that same pattern. Soon you can't tell much difference, but it's still there. Now here's your morning. All right, I got to get around. remind me? Say. A little louder. Jalen, got it. Got to find you now. There you are. All right. Okay. Now, let's look at the odd exponents. Okay? Let's look. They left off one. I'm going to put this one in. What if y was equal to x? When your exponent is 1. What would that look like? It has a special name, by the way, too. Y is equal to x. Sorry. Give me some points on y is equal to x. Second? 0, 0. Oops, I should go to dark probably. Okay. Another one. 1, 1. Minus 1, minus 1. Minus 2, minus 2. That would be, that's a linear function. Okay. It goes like that. Okay. Hits those same 3 points as the other two are hitting. Sorry. Okay. Now this one doesn't have any curvature in it. That's why they left them off. But it hits those 3 points. 0, 0, 1, 1, and negative 1, negative 1. Okay? Now, you go to the cubing function. That's the gray one here. And it's 0, 0, 1, 1, and negative 1, negative 1. Okay? But past that, the cubic function goes up, where this one just keeps going in the same direction. This bends upward. And in between minus 1 and 1 is flat, whereas the linear function is not. Okay? But when you go to the fifth power, it comes up more sharply, flattens out longer, and goes up more sharply. Just like the upper powers did here. If you went to seventh, it would be sharper here, flatter there, sharper there. 9th, 11th, 13th, and so on. Okay? So you see they follow very, very similar patterns, but every one of them goes through those 3 points right there. Of these parent functions, these power functions with odd exponents. Now, something to note. Even exponents, as long as there's no negative sign there, always positive. You square a negative number, you've got a positive number. Raise it to the 4th power, the 16th power, the 32nd power, it doesn't matter. Anytime there's an even exponent, no matter how negative you get, when you raise it to an even exponent, it's positive. However, when you raise it to an odd exponent, it's negative. Okay? Now, anything raised to a positive power, whether it's even or odd, those are always positive. Okay? I mean, not positive. Positive numbers raised to a power, they're always positive, no matter what power you use, even or odd. Okay. That's going to lead to something we're going to talk about later, so don't lose this thought. I wish they pieced it together a little better, but I guess it's as good as they can do. Okay. Moreover, the greater the value to n, the flatter it is near the origin, and the steeper it is outside plus or minus 1. No matter with even or odd exponents, flat around the origin, steeper outside plus or minus 1. Okay, so let's sketch the graph of each of these functions. All right, now what they did on this first one for you is they sort of messed around with it a little bit, didn't they? They threw in a minus sign. Okay, now is it going to help you to do the parent function first and then negate it, or can you just negate it right from the start? What do you think? Say again? I can't hear. Okay, let's do. Give me a value. Okay, well, let me throw in a few points here. 1, 2, 3, 4, 5, 6. We're not going to need that many. Give me an x. 1. Okay, oh, goodness gracious, what did you do there? There we go. All right. You put a 1 in there. 1 to the 5th power is 1. Then you negate it and you get -1. So when you go over +1, you go down to -1. Good. Give me another one. A little louder. Anyone say something? I thought someone said something. Give me another x. Feel like a cheerleader up here. Give me an x. Say again? Anybody? 4. Ooh, boy. Okay. 4 raised to the 5th power is huge. Off scale. Okay? 2. Okay? 2 to the 5th power. Anyone know? -32. And -32. So that's way off scale. -1. Okay, let's do that one. -1 to the 5th power is? -1, but then you negate it and it becomes +1. Okay, y'all left off the easy one. 0. And what does that give you? 0. And even 2 is going to be off scale. So what this function does is come down really, really, really sharply here and flatten out like crazy here, and then takes a bend and goes down very sharply there. I probably exaggerated it to some extent, but that's what it is. Okay, something like that. How is that different from the x to the 5th they had up there earlier? It's going the opposite direction. Let's go back and see. X to the 5th before was this one right here. You see it? The dark line on this side. Okay? Now it's going in the opposite direction. And I have mine a little too sharp of a turn there. It should be a little more rounded. But that's what it looks like. Okay? Can we do H on the same scale, or you want to do a new scale? It's up to you. Same? Okay, give me a different color. Second? Red. Is that what you said? Okay. Yeah. Okay. Now, how do we do this one? Now, this one, I really think it might be a good idea to do the parent function first. This is what is involved with this one. You had it on the last test, in the last chapter, in the last quiz. What's involved with that? Okay, a horizontal shift to the left 1. Exactly. So we could go from there. You want to do that? So if you go from the left 1, that means what was your 0 before is now over here at -1. And that was a 0, right? And you can plug in a -1 and see that works. -1 plus 1 is 0. 0 raised to the 4th power is 0. Right? Now, what if you had gone 1 to the right of that 0? Where would you have been? At +1. Okay? And sure enough, that works too. Because that would be at 0. 0 plus 1 is 1. 1 to the 4th is 1. What if you went 1 to the left of that 0? Like at -2. Where would you be now? Second? 1 again. Okay, let's check it and see. -2 plus 1 is -1, but -1 raised to the 4th power is 1. Okay? So these go up really steeply here. If you went to 2, one more over, like 1 plus 1 is 2, 2 to the 4th power is 16. It's already out of sight. Okay? So these come down very steep here, flatten out pretty much here, and then, whoops, and then goes up really steep there. I don't know what my little wiggle around there was doing, but it wasn't doing well. Or there. Okay. So that is your number B. That's the red one. Okay? Do you see how that works? Look at that and say, hey, that's the shift of the x to the 4th, shift to the left 1, and then you can draw your graph pretty easily. Okay? Now, any questions on that so far? Notice, even power, up and up, odd powers going in opposite directions. Hang on to that concept. We'll be there in a bit. Oh, let me erase mine so you can see how they drew theirs. Okay? So the first one, that's a reflection across the x-axis because you negated the y, and that's exactly what you got. The other one started at -1, 1, 0, +1, +1. This one reversed that and did -1, 1, and 0, 0, and +1, -1. Okay? The negative coefficient has the effect of reflecting across the x-axis. We did in chapter 1. I think it was 1.6 or somewhere back there. Maybe 1.5. I don't remember. Okay? Any questions? On the second one, they did on a separate graph, it's a horizontal shift to the left 1. So it took that quartic function and moved it 1 to the left. And you still have steep outside, plus or minus 1 from the vertex, you might say, and flat near the vertex. Okay? So it's just a left shift by 1 unit. Make sense? All right, good deal. All right. And by the way, there's a checkpoint after that example too. Please do those as soon as you can. All right. Let's get ready for the leading. I don't like to call it coefficient. They like to call it coefficient. I like to call it the leading term test. Okay? In example 1, you notice that both graphs eventually rise or fall without bound. And that's true of all polynomial functions as x moves to the left or to the right. Okay? Let's just go back and look at that. See how after a while, you don't have to get very far. X is, when x gets just a little bit large, y gets incredibly large. When x gets very large negative, y is still incredibly large. Okay? Go back to this one. They're still going very large. That one's going large positive. This is large negative. All polynomial functions do this. After some point, they go to infinity. Okay? Either positive or negative infinity. In both directions, they do that. Okay? Here, these two. Now, even my linear function there is going to positive, negative infinity. It's going there a little more slowly, but the higher order polynomial functions get there faster. See how they go up or go down very, very rapidly after a while. They fiddle around in the middle some, but after a while they're heading north or south. Okay? So that's what they're asking us to look at here. Whether the graph of a polynomial function eventually rises or falls can be determined by two things. The function's degree, whether it's positive, even, or odd, and the coefficient, the sign of the coefficient, whether it's positive or negative. Those are the two things. Now, they call it the leading coefficient test. Well, the coefficient only applies to one of those, the positive and negative. The term, the leading term, that incorporates both the degree and the sign. Okay? So that's why I don't like calling it a leading coefficient test, because the coefficient has nothing to do with power. Okay? It's just with the number. The sign is important, but it's a leading term gives you both the sign of the coefficient and the degree of the polynomial of that term, the variable. All right. So here's what the leading term test tells you. Okay? So let's start with, and what we're looking at is basically what we call end behavior. We can't tell what's going on in the middle here. It can be doing all sorts of weird things there. But what this does tell you is what goes on when x is very large, negatively or positive. Okay? So as x moves without bound to the left, which would be negative, or to the right, which is positive, the graph of the polynomial function eventually rises or falls without limit. Either one. Now, and your n is odd, 1, 3, 5, 7, 9, you know, the odd numbers here, then as x gets very large positively, now, they should have this up there too. When that leading coefficient is greater than 0 and your n is odd, when the as x goes to positive infinity, your f of x is going to positive infinity. Because any positive number raised to a very high power is going to be very, very, very positive. Okay? Okay? And any negative number raised to an odd power is going to be very, very, very negative. Okay? So as f of x goes to negative, I usually say the x first. As x goes to negative infinity, f of x is going to negative infinity. When x is going to positive infinity, f of x is going to positive infinity. By the way, get used to this. These are the things you note about the end behavior. End behavior when x is going very negative or very positive. So those are always going to be, one's going to be x going to negative infinity, x going to positive infinity. When every one of the tests for end behavior, that's going to be what the x is doing. One negative, one positive, both going to infinities. Okay? Your f's are also going to infinities. You just don't know if they're positive or negative. So guess what? When this shows up on a quiz or on a test, and it asks about the end behavior, every one of those blanks is going to have an infinity in it. Okay? The x's, one's going to be negative and one's going to be positive. So you've got most of the answers right there. The only thing that the test is telling you is whether this one's plus or minus and whether that one's plus or minus. Okay? That's what it will be telling you. So when n is odd and the leading coefficient is positive when positive and negative when negative. Okay? Just think on that. Okay. Now, again, when n is odd, but this time your a sub n is negative. That leading coefficient is negative. That flips everything over. So now this one that was going south is going north. This one that was going north is going south. Okay? So, again, notice, as x goes to minus infinity, as x goes to plus infinity. Those are always there. Those are the things you're testing. And these are both infinities. So now all you have to determine is what the sign of it. And as x goes to negative infinity here, it would normally raised to an odd power would be going negative, but if that coefficient is negative, that flips it over and turns it positive. The same thing here, when x is going positive, usually an odd coefficient is going to keep it positive, but if that leading coefficient is negative, it flips it down. So, there they are. And you will see this on every one of them, what x is doing and what f of x is doing. And every one of those is an infinity. Your x's, one's going to be negative, one's going to be positive, and then all you have to do is determine the signs of your f's. One's positive, one negative, both positive, you determine. Okay? Thanks. All right. Now, what happens if n is even? If n is even, they're going on the same direction, always. N is odd, they're going in opposite directions. F's are, okay? But notice the x's are the same. One x is negative infinity, one's positive infinity. One x is negative infinity, one's positive infinity. The x's are always that. So you should get those right every time, okay? But the question is what's happening to the f. Well, if that leading coefficient is positive, when you're raising a positive or negative number to an even power, it's always positive. So if your leading coefficient is positive, it's on the up and up. So the end behavior for an even function, positive coefficient, up and up. Positive, infinity. But if that leading coefficient is negative, because they're going the same direction, they flip them both over. And then your f's are both negative infinity. Pretty simple concept, isn't it? Okay. Now, if nothing else works for you, I'll tell you one other thing you might try, and I think it usually works pretty well for me anyway, so hopefully it would be for you too. I'll show you when we get there. So here's example 2. describe the right hand and the left hand behavior of the graph of each function. Okay? And I will write down how you describe that. Okay, let me get my pen back. Okay. Okay. Can anyone tell me what to fill in those 4 blanks? Right off the top. Give me something I can write in all 4 of those blanks. Infinity. Okay, good. Infinity. Oh, I can't write infinities very well. Something like that, something like that, something like that, and something like that. You should get that part right down. Okay? Now, where are the x's going? Where the x is going?
Negative.
1 negative, 1 positive. So you can fill that in. 1 negative, leave the other one positive. Okay. Now, all we have to determine is what in the world is the f doing. Okay. Now, let's start over somewhere else. What's your leading term in this polynomial? Negative x to the cube. The one with the maximum exponent. Exactly. Okay? And what does the cube tell you? The cube tells you they're going in opposite directions, right? Right? An odd exponent always is going in the opposite direction. We just don't know which. I feel like a semaphore. Never mind. Okay. Now, normally, if x was positive, going in the for positive infinity, this would be going to positive infinity also. Right? Anything. But when you negate it, flips it to negative. So what would this be? A negative infinity right there. Okay? Now, as x goes to negative infinity, an odd exponent would normally be going negative. So it's got to be opposite direction of this, but with that minus sign, that flips it up. So again, they're opposite from each other, so that stays positive. There you have it. Negative infinity, positive infinity. Positive infinity to negative infinity.
Does it have to be in that order?
Say again?
Does it have to be in that order?
No, you can put them in the order you want. They're usually on the test or a quiz. I'll have the blanks there. Yeah, but if you want to say plus here, you can say plus, minus, minus, plus. But you have to have one of these x's positive, one negative. I don't care which order you put them. But if this is negative, this problem, that's got to be positive. And if this is positive, in this problem, that's got to be negative. So the order matters in the pair, but which pair you put first, it doesn't matter. Is that what you're asking? All right. Let's do it for the B. Let me see if I can write from this side. I think I can. Again, we'd say as, goodness gracious, as x goes to blank, alpha of x is going to blank. As x goes to blank, alpha of x is going to blank. Okay? Anyone tell me what to fill in the blanks? Infinities everywhere. Good deal. Okay? I'm getting a little better at the infinities. Okay? Now, what else can you tell me I can do right off the top?
There are even exponents, so they're going to.
Okay, yeah, but before that, always going to be the case. Has to do with the x's.
One's going to be negative.
One's negative, one positive. Do you care? Which one you want positive and which negative? Name one. First one, which? Negative. Okay, we'll do negative and leave the other one positive. Okay. Now the question is, what are the f's doing? And what do we consider? 2 features?
What he said about the degree.
Okay, the degree is 4. Maximum exponent is 4. 4 is even. What do we know about even exponents? They're both positive. Unless that coefficient is negative, in this case it's not, so we have our answer right now, positive, positive. You see that? It's really a pretty simple concept, but I can't believe how many people will get this messed up. Okay? Now later, when we do rational functions, sometimes you're approaching other things. Because rational functions have these asymptotes and things like this, so you have something that looks like this, but you're approaching different values. That could get a little confusing, but right now, this is pretty straightforward. That won't be until section 6, okay? So here for f of x equal x to the 5th minus x, again, we'll do as x approaches blank, f of x approaches blank. And as x approaches blank, f of x approaches blank. Okay? Anyone tell me how I can fill in those blanks? Infinities all the way around. Okay? So that'll be an infinity, an infinity, an infinity, and an infinity. Okay? What else can I put on right at the start before I even start thinking about things? One of what? One of the x's is negative and one is positive. Which one do you want? First one, which? Negative. Why not? You like the way I did it the first time. Okay. So, that part you can do right off the top, and all you have to figure out are the signs of your f now. Okay? Now, what do you consider when you're considering those signs? Two things, two features. The exponent, maximum exponent, which is a 5, which is odd, and the sign of the coefficient, which is positive. Okay? So what do big numbers do? Do you want to start with the small or the big? We started with the small. Very negative numbers, what do they do when you raise them to an odd power? Negative numbers raised to an odd power. Then go really negative. Because think about it. Minus times minus is plus times minus is minus times minus is plus times minus is minus. Every other one, so the odds are always opposite sign. Okay. So this would be going negative normally. What's the sign? Positive, so that means it goes negative. So then you can fill in the minus there. Okay? And if x is going positive, very, very positive, large number, what happens to your f? Yeah, it's positive, and the coefficient is positive, so that stays positive, leave it alone. You can put a plus sign in there if you want to, that's fine. But don't put a minus sign. Okay. Got it? Now here's the other way. If you don't like to remember the rules that way, here's something else I do. And you decide whether you want to. Okay, let's take a fairly negative x. Now don't change this. Leave the infinities there. But let's just take a fairly negative x, but not too big, like minus 10. Okay? If you do a minus 10 and raise it to the third power, what does that give you? Anyone know it? 10 to the third power is 1,000, and minus 10 to the third power would be negative 1,000. Then you negate that, it's positive 1,000. To me, that's a pretty positive number, a very positive number. Okay? And then do positive 1,000, that would be, positive 10, that would be a positive 1,000, and then negate that, and it goes negative 1,000. So that's a negative thing. So if that helps better than trying to remember the rules for positive and negative, just plug in a large positive number, large negative number. Okay? I like 10 because it's easy to reset the powers. Okay? Whatever. You see how to do this? Now that's my way. I don't know if the book does, but let's see how the book does. Any questions before I erase this? Yes.
So whenever your x is negative, like you get to pick one. So you plug in that negative x, and that'll find that f of x, right?
Yeah, exactly. Yeah. And that's why if you don't want to remember rules, just imagine that's a minus 10. do this to it and see what happens. It comes out positive 1,000. That's pretty positive toward it. Okay. Big negative number, big positive number. Okay. Any other questions? Good questions, by the way. All right. This is called end behavior. What happens out here? In the middle, we got to worry with later, but right now we're dealing with end behavior. Okay? So they drew the graph, which is fine with me. If you have a graphing calculator, that would be fine. Remember what we said before? What was the feature of this function right here? We didn't talk about it now, but we did earlier. What can you tell me about that function? Okay, okay. Maybe some things like that, but let's think. What's the exponent here? And here? So what kind of function is this? An odd function. And what's true of odd functions? Whatever goes on here, the opposite goes on here. And look at this. When this goes up, that goes down. This goes up that high, it goes down that low. This goes down, this goes up. So there's another feature you can pull into play when it fits. It just happens to fit on this one. So I thought I'd remind you of that. Okay? What's happening with x when x goes very negative? F of x is going very positive. When x goes very positive, f of x is going very negative. Why? Odd exponent, they're going in the opposite directions. The minus sign makes it flip over and go in the opposite direction of the x. Does that make sense? Now, all they do is say it rises to the left and falls to the right. That's okay, but why not do your little 4 blanks and you know what those should come out being. And otherwise sometimes we get a little confused with rising and falling, but anyway. All right, the second one, what kind of function is that? Even. That's even, that's even. Is that even? No, that's x to the 0th power, isn't it? Because x to the 0th is 1. So yeah, that's even too. So this should be the same on both sides, and look at that. Exactly the same on both sides. So that happens to be an even function. And because the leading coefficient is positive, that's on the up and up. Okay? Make sense? Our analysis gave you the same answer. So if you want to graph them, if you have a graphing calculator, you know how to use them, you can use that as a tool. What you have to do is fiddle around with your scales and make sure you got the full function. So sometimes that you might miss that, but if you analyze it the way we did, even or odd exponent, even or odd exponent, positive or negative coefficient. That will tell you everything you need to know about end behavior. Okay, how about this one? What kind of function is that? Odd, that side and that side. This is so bizarre. Most of the time, most of your functions are going to be neither, okay? These just happen to give you 3 that were all odd. It doesn't matter. All you're interested in is that leading term, the leading exponent, okay, the degree. Because the degree is odd, they're going in opposite directions. Because the leading coefficient is positive, negative is going negative, positive is going positive. So they have the same sign in both directions. Does that make sense? Okay. Now, in that example we just did, note that the leading coefficient test tells you only whether the graph eventually rises or falls going both directions. Okay? It doesn't tell you what's going on in the middle. That's what we're going to be studying later. Okay? Other characteristics of the graph, such as intercepts. What kind of intercepts can we have? There's 2 kinds. X-intercepts, Y-intercepts. How many X-intercepts could you have? You could have none. 1, 2, 3, 4. Okay? You could have many X-intercepts. How many Y-intercepts could you have? Second? 1 and only 1. Or 0. You may have 0 Y-intercepts. You can't have more than 1. Why? What is the Y-axis? vertical line. And what does the vertical line test tell you? A function can't cross a vertical line more than once. So you can only have one y-intercept. You may have none. You can have many x-intercepts. Okay, minimum and maximum points. We saw those in quadratic functions. They were easy. In these higher order, not going to be as easy. But you know what they are. Okay? So these you're going to determine by other tests. The end behavior is just your leading term test. Everything else you got to do something else to get. Okay? So, let me make sure that I'm not skipping something here. There was example 2. Yeah, we're in the right place. Okay. All right. Real zeros of polynomial functions. What is that going to tell you? The zeros of a polynomial function. The x-intercept. Perfect. The zeros of a polynomial function will be the x-intercepts of that function. So you'll know where to plot those on the x-axis. Okay? It can be shown that for a polynomial function of degree n, the following statements are true. So hang on to these, folks. If your function has degree n, the function has at most n real zeros. In other words, can't have more than n x-intercepts. Okay? Let's go back and look. Okay? What was the n of that function there? 5. It can't have more than 5 x-intercepts. How many does it have? 3. Okay, that's not more than 5. Okay? This one, what's the n? 4. How many x-intercepts could it have, or zeros? Up to 4. How many does it have? Exactly 4. Now what that tells you is that if you're looking for your zeros, and it's the 4th degree, you find 4 of them, don't look any further. Don't say, well, it could come back down somewhere here. No, it can't. If this is a 4th degree polynomial, it cannot have more than 4 intercepts. Okay? What does that tell you? 3. You found 3, stop looking. It can't have more than 3. Does that make sense? So you see, here's something else that we can figure out fairly simply. We can't tell how many it has, but we can tell the maximum that it could have. So if you find that many, stop looking. Okay? Now, if it has degree n, then the most number of terms that could be max or mins would be n minus 1. Let's see if that works. Okay? What's the n here? 5. 5 minus 1 would be 4. It can't have more than 4 changes of direction. This one has 2. Okay, that's not more than 4. This one, maximum, 4. 4 minus 1 is 3. How many changes of direction? 1, 2, 3. That's all it can have. It can't possibly come up here and come down again. It can't happen because of that second rule. Okay? How about this one? Degree? 3. How many turns can it have? At most 2. And it has 2. Don't look any further. It cannot possibly come up again or go down again. It can't do it. The maximum has been reached. Okay? So that's what the second one tells you. Okay? If it has degree n, the most number of turning points it can have is n minus 1. It may have fewer than that, but it can't have more than that. Okay, and we also call those relative minimum or relative maximum. There's a reason for that too. And if you think about it, it makes perfect sense. Okay. Do you think that is an absolute maximum? No. Polynomial functions are going to infinity somewhere. Okay? Is that an absolute minimum? No. It could be going to negative infinity. So it can't be absolute, but it's a relative maximum and a relative minimum. That's why we use those terms. Okay. Now, Most of the rest of this section, I think into the next section, is going to be dealing with finding those zeros. Because finding the zeros of the polynomial function is one of the most important problems in algebra. Okay? Usually that tells you where your turning point from loss to profit is. That tells you where, various things, where things are making a difference. Okay? So there's a strong interplay between the graphical and algebraic approaches. Okay? This is probably the last slide we'll have today. These 5 statements are all equivalent. If one of these is true, of these 4 statements, I can't count. If one of them is true, the other 3 are true, without doubt. Okay? First, if x equal a is a zero of the function, if that is a zero of the function, then x equal a is a solution of that. Well, that's how we found our zeros, right? If you were given a function, you want to find the zero, set the function equals 0, solve it. Okay? So that means if that is a solution, that's a 0. If that's a 0, it's a solution. Okay? If that is a solution, x equal a is a solution to that, then you can subtract a from both sides and have x minus a would be a factor of that polynomial f of x. Well, of course, that's how we did. When we solved this equation, if we could factor it, you got the factors, and one of those was x minus a, we set it equal to 0 and found out x equal a. Yeah, we've been doing that. So these 3 are all equivalent. And the one other that you just said, someone mentioned it before, if x equal a is a solution or a 0, then a 0 is an x-intercept. Those are your x-intercepts. And if that's an x-intercept, there's a factor, there's a solution, there's a 0. You know all of them if you know any one of them. Okay? Now, the next thing we'll do is example 3. I'm afraid we don't have time for example 3, so we'll start that next time. So but before you go, let me give you some homework exercises, because I know you'd be really angry with me if you had a whole weekend on your hand and didn't have a single math problem to do. So please don't get angry with me. Let me give you some. All right. Here we go. Ooh, this is a long section, folks. All right. I think you can do every one of 9 through 14. The odds are in the back of the book and at calcchat.com, but I think you can do every one of them. Okay? And you I think you can do any of either 15 or 17. They're both at CalcChat. 17 is at CalcView. I know you can do any of the odds 19 to 27. They're all at CalcChat. 21's at CalcView. If you have a graphing calculator, try doing 29 and 31. They should both be at CalcChat. All right, and we will stop there and pick up the rest of those next time. Okay, good deal. You're all happy with me now, right? Good, all right. All right, have a good weekend, and of course, working pre-calculus problems. We'll make it a good weekend, won't it? Yes, okay. Good deal. All right, now I meant to say this too, folks. I still don't have all your tests graded, but I'm hoping this weekend finally to have some time to get those done. If I'm here on Bethel campus tomorrow, I hope I won't have that many interruptions so I can get some of them done. I'm still working on spring schedule and fall schedule, though. That's going to set me back.